Swayam Prabha. Digital India. Educated India.
So we started discussing about chemical master equation in the last class. So this is a framework to discuss a jump Markov process, and we started off with an example of a reaction A going to B. Sort of a first order reaction with a rate constant K. And then for us the stochastic variable n is basically the number of molecules of A. Okay, since the number of molecules of A and number of molecules of B, they are related by the initial condition, we have only one random variable to describe this network. If I know n, I can know what is nb. Okay, and the initial condition for this is that okay, when n is equal to n naught, this is the total number of A molecule present at time t equal to 0. Okay, so the initial condition is described like this. Then so what we have done, we have actually given a reaction scheme. Initial condition, generally initial condition is given in terms of number of molecules, but here we are saying what's the probability of finding the number of molecules, and we say that probability is 1 if n is equal to n naught. Okay, so this is a probabilistic way of describing the initial condition. So then what we did was we wrote the chemical master equation for this problem. Okay, so here when we look at the transition probability W, we have only cases where either n plus 1 can become n or n can become n minus 1. Okay, these are the possible events that affects the state of n. The state with the number of molecules n can be created by a reaction happening with n plus 1 going to n, or you can have a state that is destroyed, the probability that is decreased when the state at n follows a reaction leading to n minus 1. Okay, these are the two processes that affects the probability of the state containing n number of molecules. Okay, so these basically capture those events. Okay, so this particular part tells you that the rate of generation of Pn due to a reaction at state n plus 1 giving to n, and this is a loss of probability for a reaction that happens through this mechanism. Okay, so we have included this. This is probably the most simplest thing you can think of. Then we want to solve this problem. Okay, so to solve this problem, we define a generating function. G of s comma t. Okay, so we define a generating function g in terms of a sum over Sn Pn comma t. S is a new variable we are introducing. Okay, by this definition, what we are hoping is to convert this function, which is written in terms of n, into something of s. So when we do this, I think we looked at okay, so we basically, yeah. Why can't I do that? Because all I'm trying to do here is I have a function p as a function of n, okay, and I'm defining a new function s such as this. Remember how we write Fourier's transformation or Laplace transformation? where you convert a time domain into a S domain or Z domain or Fourier domain. Like that, here we are defining a function. Okay, this definition leads to converting the variable n into S and T. Okay, so that's all. So we are basically mapping n, which is a discrete variable, into another variable which is S. By doing this, why we are doing this? We are doing this because if you look at this, this is a recursive differential equation. Okay, you can write dp1 by d2, dp2 by d2, and you can go all the way up to very large number. Yeah, but you have to keep writing it, right? As a function of different n values, we'll have to write n number of differential equation, right? So you'll have to write dp1 by dt, some finite terms will be there. Then dp2 by dt, you'll have some finite number. So if you are willing to do a numerical approach, then you can go about this. You can actually set out thousands of ODEs, use some discretization method, and you can go about solving it. But here we are trying to get an analytical result, and this is one particular way. Now, when I have little complicated terms here, okay, when you have a very complex networks, you'll have a little bit more complicated nonlinear terms and mixed terms. In such a cases, even this approach may not be useful. Then you have to resort to a numerical approach. In the numerical approach, you don't need any of this. You can write an array of differential equations. Simultaneously, you can solve them numerically. Okay, that approach is anyways there. Here, what we are saying is, for a simple reaction network like this, we can apply some of the known mathematical techniques to arrive at an analytical expression. Okay, so that's all. Okay, so we are basically converting this chemical master equation into this generating function formula. Okay, so all we are saying is the P, which is the probability for finding number of molecules n at time t, is now mapped into another function G, and the relationship between G and P is this. Okay, so this definition is important because we'll come back and then we try to retrieve what P is by looking at this. Okay, in other words, what I'm trying to do here is I define a mapping function. Using this mapping function, I want to rewrite this differential equation. That's what I got here. This basically gives me a simple linear first order partial differential equation. I'm going to solve this. Once I solve, I'll get G of s comma t. Okay, a solution of this will give me G of s comma t. Then I will look at this formula, this function, and then I compare with this function, and then by matching the coefficients, suppose let's say this has some sum over, I'll show you this soon. When you have a solution of G of s comma t by solving this in this particular form, let's say, so then I compare the definition with this. Whatever I see in this bracket here should be equal to P of n comma t, right? When I match this solution arrived from this and then match with the definition, by comparing the coefficients of these two expressions, P of n comma t is nothing but the bracket that the term that I want to see in this bracket. Okay, so my ambition now is to derive an analytical expression for G of st and then post it in this particular form. Then compare the coefficients of s power n and then say what is P of n comma t. So instead of directly solving this, what we are doing is we are mapping into a generating function, and then with respect to the generating function come to a analytically soluble differential equation, partial differential equation, solve it, and then put it in a form that actually confines that compares to the definition itself, and then by matching the coefficients I will get what is P of n comma t. Okay, so that's what we want to do here. Okay, so to save time, what I'll do is I've given all the details in the notes. I will write the equation, the final equation that you will get by solving this. This is what you will get. Okay, so what you will have is you will have this equation and then use methods of characteristics or methods of line by defining a variable z in which s and t are mapped into, and then if you process that, you will be able to show G of s comma t follows this. So now you see that I was telling you that I want this expression to be written in this form, but that they are not in this form, right? So now what we want to do is to kind of change this formula a little differently, and then bring it to this kind of form. So in order to do that, what I'm going to do is I'm going to expand this using a binomial theorem. Okay, so binomial theorem, as you know, so if I have two terms a and b to the power m, this can be written as so a plus b power m can be expanded sum over I is equal to 0 to m, a combinatorial term of m and I, a power I and b power m minus I. Okay, so I is a index here that goes from 0 to m. So basically you can expand this. Okay, you can expand this, and that's what this function is going to be. So why I am doing this, because I want to use this expression and write it in this form. So before we apply this, so let's take this one. 1 plus s minus 1 e power minus kt So here I am writing this term that multiplies s separately. And the remaining terms are 1 minus e power minus kt. So this is like component A for me, and this is like component B. Okay, and then this is power raised to the power n0. Okay, so therefore, what we can do is 1 minus e power minus kt plus s e power minus kt power n naught can be written as n is equal to 0 to n naught So this function g of s comma t is given by this expression. Now this expression is split into this form. Okay, so now I am applying this binomial theorem to expand a plus b power n as sum over n is equal to 0 to n naught, the combinatorial term n naught n. This is a power n, b power n0 minus n, and that is equal to g of s comma t. Maybe it is better if I write this way. This is n and this is n0 minus n. Okay, it doesn't matter which one I call A or which one I call B. Okay, so now what we will do, we will take this expression So here I take s power n outside, and then the remaining terms are this prefactor e power minus kt power n and 1 minus e power kt n0 minus n, and this is actually g of s comma t. Okay, so this is the solution that we have got now. Now if you compare that with the definition that we started off with, okay, so we basically have got a g of st analytical function that actually looks very similar to this definition itself. There is a summation from n0 to infinity. So here we wrote up to infinity, but actually n can only go up to n naught, the initial number, and then it can only decay. So what we actually mean from n is equal to 0 to infinity basically means n is equal to 0 to actually n naught. It cannot go beyond that because n cannot exceed the initial number n naught. So we deal with that initial term. Then you have s power n, and then whatever that is remaining here, that entire thing is nothing but p of n comma t. So by matching the coefficients of s power n, we say that the p of n comma t is basically a binomial random variable. So going back to this reaction A going to B, starting with n0 number of A molecules, this probability function tells you that as a function of time t, how n is going to vary, okay, and that is basically a binomially distributed random variable. So in a way that this gives the probability of reaction probability to react, and this gives the probability not to react for no reaction. So even though we wrote this is p of n comma t, but remember this is also a conditional probability, condition with respect to the initial condition, that is n naught comma 0. So we should be writing that as in this form, because for the brevity we actually drop this extra terms, but actually what it means is that expression is valid only for an initial condition at time t equal to 0, there is n0 number of A molecules. Now with this form, we can also write a transition probability that if I have n prime and at t prime, okay, if I have n prime number of molecules at a t prime, provided that n prime is larger than n, okay, because n can only decrease from, and then t is larger than t prime. Okay, so when time increases from t prime to t, and n can only decrease from here, so this has to be more than this, and then now we can write a transition probability for a given n at a given time, and then asking the probability of n and t at a different time. Okay, so from here we can replace n naught with n prime. So this would be the transition probability between two time intervals, t and t prime. So this gives actually the entire distribution that we are looking for, but generally from an experimental point of view, we are interested in some statistical quantities like mean, standard deviation and so on. So it's true. This must be t minus t dash. Okay. Yes, it must be like this. Yes. or the other way around, right? T minus, okay, T minus, yeah. And this also should be n prime. Okay, please check if this is okay. And this is the transition probability. Okay, so as I was saying that we can work with this entire distribution, or if you want to look at only statistical quantities like mean and the standard deviation, so on, so we can directly write that for this distribution, which is a binomial, the mean, okay, is nothing but n naught times minus kt and then standard deviation is square root of mean square minus square of the mean. This is the standard deviation. And if you are interested in the coefficient of variation, which is mean divided by the standard deviation, we can find that sorry, the other way around. The coefficient of variation is defined as standard deviation by mean. So n naught e power minus kt So standard deviation with respect to the mean will scale as 1 by square root of n naught. Okay, what this means is if you have a reaction that has n0 initial number of molecules, if this number is very large, okay, when I say very large, let's say you're talking about 1 moles of substance in reaction mixture, then n0 is of the order of 10 power 23 Avogadro number, right? So then this fluctuation 10 to 0, that means you will not see any signature of stochasticity in a large sample that you are looking at. So that's where the deterministic approach is valid, where the concentration or number of molecule looks like a continuous variable. The fluctuations are not detectable. But suppose if n0 is a small quantity, let's say 100, okay, so then this standard deviation with respect to mean can be a very large quantity, okay, it can be about 10% of the mean itself. So the stochasticity or the fluctuation becomes very significant and apparent when we deal with a very small system size, okay, and the evidence is here. The fluctuation that you're going to see is going to be proportional to inverse of square root of n naught. So if I look at this mean itself, okay, and if I non-dimensionalize this with respect to n naught, then this is basically the mean is going to change as exponential of e power minus kt. So as a function of t, you will see as an exponential decay. This decay depends on the rate constant k, and k itself is dependent on temperature. Okay, so once the temperature is kept constant, then the k is constant. So you'll have this kind of a exponential decay of number of molecules of A as a function of time. Now on the other hand, if I wanted to look at this quantity, that standard deviation with respect to mean or the coefficient of variation, then this depends on what n0 I'm going to look at. Okay, so here what will happen is you get this for n0 is equal to 1000. This is for 10 power 4. Only when we go to something like 10 power 8, that this so all the red curves that you see here, these are all sigma by mean, okay, coefficient of variation. When the number of molecules are very large, like 10 power 8 or so, the coefficient of variation is nearly 0. Okay, so this is where the deterministic picture is valid. But when you go long time, the number of molecule itself comes down because things are reacting away, and you see regardless of this n, the error, the standard deviation with respect to the mean will always grow. Okay, so the way to look at this data is, suppose if I have a starting of n0 number of molecules, mean is given by this curve, but at every point, at this point, the error bar is this. When I go here, the error bar is actually increased. When I go here, it actually increases even beyond, and so on. Okay, this is because as the number of molecules decaying, the coefficient of variation increases. That means this error bar that we see here, the standard deviation that we see here, will increase. On the other hand, if I start with the n0 equal to 10 power 8, then these error bars are going to be very small, that you can approximate this to a deterministic equation. So the mean, the normalized mean n by n naught is e power minus kt. That is this curve. Since I am normalizing with respect to n naught, this curve does not change when I change n naught because it's already normalized. On the other hand, if I plot the coefficient of variation that is given by this expression, 1 minus square root of 1 minus e power minus kt divided by n0 e power minus kt. So this function depends on n naught. Okay, even because we are only normalizing this with respect to mean, not n naught. So therefore, the coefficient of variation will depend on the initial number of molecules, n naught. So these curves that you see here, these are all for different initial conditions. This is for 1000 initial molecules. This is for some 10,000 initial molecules. This is some 10 power 8 initial molecules. As a function of time, this is how the standard deviation or the coefficient of variation changes. Now what we are saying is that these curves, okay, basically signifies the error in the mean. Generally we look at only the mean, we don't say about the error bar. So now we are saying that depending upon the initial condition, the uncertainty or the fluctuation about the mean is going to grow if you have a very small number of molecules to start with. So suppose if I take this point, this is a mean, and I want to know what is uncertainty there. To answer that question, I have to say what is the initial number of molecules. Let's say I start with the 10 power 3 molecules. So this is the curve for 10 power 3, and I read the value of this point, and this is what the length of this. Okay, similarly I go to this point, this is mean is predicted. What about the standard deviation? Standard deviation at this point should be this. Compared to this point, here the fluctuation has grown, the size of the uncertainty is grown, and when you go larger, smaller and smaller time, this become more and more uncertain. Meaning when you do an experiment, when you try to detect the concentration of the molecule, as you go to longer and longer time, you become more and more uncertain about the mean value. You can get a mean value, but it's going to fluctuate a lot. Okay, now we are saying if the starting number of molecules 10 power 8, like here, then you see that the standard deviation or the fluctuation is going to be very small. Okay, so if I take 10 power 8 as my initial condition, when I go to mean value here, the fluctuation is actually smaller than the point itself. So you'll assume as if it's a deterministic variable. There's no fluctuation. It is deterministic. When I go here, again this is very small to 0. You will not see any fluctuation unless you go to somewhere here where it starts growing. Okay, so that's the meaning of this plots. So just to recapitulate what we did, so we looked at the chemical master equation for a jump Markov process, and then we applied this framework for a simple reaction A going to B. We defined the initial conditions, and then we wrote the specific forms of the master equation, and then we used some mathematical tool to solve it. By this method, we arrived at the probability distribution function itself for the number of molecules of A, which is a binomial random variable. Once we have the form binomial random variable, we can get all the statistical quantities we want. Here we looked at only the mean and standard deviation, because these are something experimentally one can measure. But if you want higher order moments, autocorrelation functions and other stuff, once you have P of n comma t, you have access to every other statistical quantity that you want. Okay, so the use of this model is only limited by what you can measure in experiment. You make any measurement that depends on certain statistical quantity, we have a model to compare with. Okay, so now if our initial objective is only to get the mean and standard deviation, if that is the case, we don't have to really go all the way to getting P of n comma t and show what the binomial theorem. Even from the generating function, we can directly get mean and standard deviation also, if that is the only thing that we want. If you don't want the absolute functional form of the probability distribution function, but you are only interested in the mean and standard deviation, we don't need to solve all the way up to P of n comma t. Even with the generating function itself, you can create expressions for mean and standard deviation. Okay, this is a small mathematical trick I'm going to discuss. This is very useful if you are only looking at mean and standard deviation and not the absolute probability distribution functions. This is not really essential, but it's probably a nice tool to know. So we'll start again from the definition of generating function. And then take the first derivative of g with respect to s. Right? Let's say I want to calculate this property at s is equal to 1. Dou g by dou a. If I calculate the derivative at s equal to 1, what is this? What is this quantity? Expected value or the mean, isn't it? So this is nothing but my mean. So if I'm interested in getting the mean value, all I need to do is get the first derivative of g with respect to s and then evaluate that differential at s equal to 1. Now let's say we want to look at also the standard deviation for n. So for that we will look at the second derivative of s. From here. So the second derivative gives this n square minus n multiplied by s power n minus 2 p of n comma t. Now if I calculate the second derivative of g with respect to s at s is equal to 1, then I get n square minus n p of n comma t. So I can write this as n square p of n comma t minus n p of n comma t. So this is mean square and this is just mean itself. So that is mean square is equal to the second derivative of g with respect to s calculated s equal to 1 plus the first derivative. So for this term plus this term, and this term is nothing but the derivative of g with respect to s at s is equal to 1. Okay. We got both of this. So now so we already know what is g in terms of s and t. Okay, this expression we already know. Now all you have to do is, if you want to get the mean, you take the derivative of g with respect to s and calculate s is equal to 1, and that will give you mean. And if you want to get the variance or standard deviation, you're going to apply this formula, take the second derivative and calculate it s is equal to 1. So let's look at what we have got for dou g by dou s at s is equal to 1. So when you calculate s is equal to 1, this entire term will vanish. So you'll have only n naught into e power minus kt, and this is your mean, by the way. So we substitute all these derivatives that we found here in this expression. So we'll get the same results. So we talked about two approaches. One approach is to get the entire probability distribution function directly, and then from there you do whatever you want to calculate, mean, standard deviation, or you stop at when you calculate when you derive the expression for S, which is somewhere here. Okay. So at this point itself, instead of going further to get P of n comma d, you can even get the mean and standard deviation by the derivatives of this function itself. So we showed that the mean is given by the first derivative of g with respect to s, calculated s is equal to 1. Since we know g, we can directly get the derivative and then get mean. Similarly, the standard deviation or the variance is proportional to all this second derivative and first derivative. Get all the second derivative, first derivative, substitute here, you will get the same result. So we have two approaches, depending upon whether you want the absolute probability distribution or you want to get only the mean and standard deviations. Okay, so you can go further and you can say, if you want to get the third moment and fourth moment, you can use the generating function. That's why it's called generating function, because it generates the moments of all the underlying probability distribution function, even though we have looked at only the first and second. Okay, so that's the very nature why we call this as a generating function. All right, okay, so we'll stop here.